the cookie. Big button in the middle moves forward, bottom one moves backwards. And if you hold down the top button, you'll get your pointer.
Okay. Okay. Thanks. Okay. Hello everyone. Yeah, it's a great pleasure to be here, and also thank the organizers for hosting this wonderful conference. And so I'm from University Sherbrooke. I just started there as an assistant professor there. So, so today I'll tell you some of our recent work on early fault tolerant quantum computation. So it's a simple quantum phase estimation algorithm based on compressed sensing. So here, just an overview, like why do we care about early fault tolerant quantum computation? So as you all know, right now we are still in the niche area, and where we have some small or intermediate scale quantum computers, but they're noisy, and they're useful for scientific or algorithmic explorations, and possibly have some moderate quantum speed ups for some maybe contrived problems like the sampling problem. But to gain real useful quantum advantage, we'll probably need quantum error corrections. And before we get fully fault tolerant large scale quantum computers, and most likely in the next decade, we hopefully will have some small fault tolerant quantum computers first. And it is important to think about what kind of algorithms we can run on these small fault tolerant quantum computers. Here, what are the assumptions when we think about algorithm design for early fault tolerant quantum computers? So the assumptions here, again, is the number of logical qubits, they're still limited, and also the circuit depth is also limited. And the objective is to design still hybrid quantum classical algorithms, but in contrast to many of the near-term quantum algorithms, we want to show that you can prove that it has guaranteed performance or advantages. The key to achieve this is to find the trade-off between the following computational resources: so number of qubits, circuit depth, and the sample complexity, and also the cost of classical post-processing. So as you can see along this list, the cost also goes down as well. So we still need to find the balance between these resources. So here, just a brief overview of the work that I'm going to talk about. So it's a simple and robust quantum phase estimation algorithm based on concurrent sensing. And we have a new version coming soon, but the old version can have some of the results I'm talking about. We showed that it achieves the Hilbert limit. Here, by Hilbert limits, I mean for desired accuracy epsilon, the total runtime is roughly 0.1 over epsilon with some polyload factors. And the quantum circuit we're going to use is very simple, as I'll show you in the next slide, in a few slides. And it is suitable for early fault tolerant quantum computers. And also in terms of performance-wise, we show numerically it's comparable to other state-of-art early fault tolerant QP algorithms with a few unique features like related to concurrent sensing. So in the next few slides, I'll explain what quantum phase estimation is for people who are not familiar. For people who are familiar, you can ignore this part. And also what is concurrent sensing, probably most people are not familiar. So I spent a bit more time on that. So, so what is quantum phase estimation? It is a procedure to estimate the phase or the eigenvalue of a unitary. More precisely, here given the unitary U and the one of its eigenvectors phi. And the objective of QP is to estimate the phase theta with high probability, given a like accuracy guarantee. QP is one of the most important quantum subroutines in quantum computation, as most of you know. It's used in Shor's factoring algorithm and the HHL algorithm for solving system of linear equations, and also for ground state energy estimation, and also for some engineer applications. It's basically maybe the most important. Yeah. So shown here is the textbook QP you probably you see it you saw it before. So here the textbook could be you can implement on a fully fault tolerant large scale quantum computers. But for a early fault tolerant quantum computer, this is too much, as the quantum circuit is too complicated. And the main two issues is one is we require many these ancillary qubits, the error corrected logical qubits. And also another thing we need is the inverse quantum Fourier transform. That's too much for early fault tolerant quantum computers. So we try to, basically the idea is try to trade time for space and use a simpler quantum circuit, but you collect the measurement results and you do post-processing. So the basic idea of this work and also many related recent work on quantum phase estimation is to use the Harman test and plus a post-processing algorithms. This you can also view it as some variants of Kitaev's original iterative QP algorithm, but with some modification. So here, as shown here, is the Harman test. So we have just one ancillary qubit and one control unitary operation. And here W can choose the identity gates, that's you measure in X basis, or the S gates, then you measure in the Y basis. So we can use Harman test to, by you measure in the X and the Y basis, you can estimate the approximate value of the unitary, the expectation value of the unitary. And here assume the unitary is some evolution operator under some Hamiltonian H, where H is Hermitian and has eigendecomposition. And we can basically the expectation value of the unitary can be rewritten as a signal, like in signal analysis. Basically here, this part is just the overlap of the initial state and the eigenstate. And also this you can treat as just some kind of probability in signal analysis. And these are the frequencies, these eigenvalues are what we're interested in. And this time here, t, is just with different time t, then we can have different signals. And from those signals, we do post-processing and to recover the eigenvalues. So in next few slides, I'd explain a little bit what computer sensing is. Computer sensing is an efficient signal processing technique for reconstructing a sparse signal. So intuitively, so the computer sensing basically takes advantage of the fact that if your signal is sparse, then you don't need like sample the whole size of the signal, and you only need to sample the compressor size of the signal. So computer sensing is advantageous whenever signals are sparse in a known basis, and when the measurements they're expensive, so you want to take as few measurements as possible, and the post-processing is cheap relatively. So this, in some sense, it's perfect for quantum phase estimation in some situations. So some situations meaning that we only care about a few dominant signals instead of the whole spectrum. And this is and considering for the early fault tolerant regime and the measurements, they're not cheap. Every time you need to rerun the quantum circuit, you need to collaborate, etc. So we want to take the measurements as few as possible. And also another thing is we can't sample in terms of times. We want to sample as few as possible. Because for those times, if you sample the bigger time, you have a deeper quantum circuit to run. And relatively, the post-processing here, as I've shown in a few slides, for computer sensing, we only need to solve a linear programming problem or a quadratic programming problem. It's relatively easy to solve. So here, just to show you a picture that show you what computer sensing can do, why it's so powerful. As you can see, for the first two these images, their signal is quite simple. It's very sparse. And with only 20% of the measurement, you can recover basically the most feature of the original image. And with 40%, you get even better. So, and the computer sensing is also used in the medical equipment to reconstruct medical images. Mathematically, computer sensing is about recovering a unique sparse solution to an underdetermined linear system by optimizing the L1 norm of X. I will explain why it's L1 norm, not L2, not the other one. And here we assume this F is some kind of measurement matrix. You can think that as Fourier matrix. And it could be other measurement matrix as well. And Y is the sampled values, and X is the one we try to recover. We have some assumptions on the measurement matrix, and with the assumption, it's called RIP, restricted isometry property in computer sensing. We can recover a unique sparse solution signal by optimizing the L1 norm. And so here I just want to show you why L1 norm, not the other L2 norm, why L1, yeah. So here I'll just show you a low dimensional example. So suppose we have this linear system Ax equal to B, and if we we know X is small, then we can have our best guess is we solve the least square problem, which you can get by optimizing the L2 norm. But as you can see, although this is this square solution touch the line, but it's not sparse. The sparse solution is roughly here or here. But like we have some assumption on the sampling, so the sparse solution is actually by optimizing the L1 norm, where you have the intersection with the line here, you get the sparse solution. So that's basically one simple example to show you why the L1 norm is kind of the key actually to the to computer sensing. And come back to for quantum phase estimation, here we assume the matrix is a Fourier matrix. And there's the time domain signal I showed earlier from the Hartman test. And if we assume these frequencies that we're interested in, they're on grid for now, just to show you the bigger picture. For now, they're on grid, meaning that they're very simple in something. All the frequencies, they equal to K over capital N for some K. And with that, the frequency domain signal can be written as such. Here is the delta function. And these two signals, they are connected by the Fourier matrix. And here we assume the signal is sparse. Basically, the frequency number frequency is roughly log capital N. And in computer sensing, we only need to sample roughly log capital N samples. This basically is in the Hartman test is the time that we're sampling. And the objective or the goal of the computer sensing is to recover the frequency domain signal by very few time domain signal by solving the following optimization problem. So here again, this as you can think as is the here is the X. And here the linear constraints here shown here, it's so when you sample, then you have it has to be consistent with the sampled value. And this problem is you optimize the L1 norm, which actually you can rewrite it as a linear programming problem, which is very easy to solve. And from the solution, then with here, there's capital N, roughly you recover the X. And so this is, of course, it's very ideal. We assume it's on grid, we assume there's noise. So next I'll just deal with these two problems, when it's off grid and when it has noise and when it's off grid. So computer sensing with noise, if our sampled value from the Hartman test, you have some noise factor Zn there, and there's some bound over there, of course, cannot be like too large. And the signals can still be recovered by solving the quadratic programming problem, which is a relaxation of the linear programming problem we saw before. So basically, we just say these two, there's a bound by some constant eta. So that's with noise. And the next one is with the on-grid assumption. So for vanilla computer sensing, signals are assumed to be on the grid. So here we assume F is equal to K over N, but in many scenarios, F could be continuous. So there's a gap between the reality and the discrete model we use in computer sensing. So this is also called the basis mismatch problem. So our algorithm, like a modified computer sensing algorithm, solves the basis mismatch problem for some special cases, which include QP. Of course, we also assume certain assumptions on the dominant part of the signal. I'll give a little bit more detail in the next slide. Here are different scenarios. So for the first one, when the frequencies, the dominant one that we're interested, they're all nearly on grid. They have some small deviation from this on grid assumption. And the noise is bounded by constant. And we show that the computer sensing algorithm can still recover all the frequencies with log n time samples. And furthermore, without any prior knowledge about the frequencies, F could be off-grid. We introduce a grid shift parameter new, such as we shifted the signal a little bit, and the dominant frequency can become nearly on grid. Of course, here we have some assumption that the off-grid components cannot be too large for this to work, and or if that's not the case, and but so in the first assumption here, we don't really assume too much about the initial state overlap. But in the second one, if we know we have a large overlap with the initial state, then we can just focus on the dominant frequency. And again, to do a grid shift, then we can make the dominant frequency nearly on grid. Then we can still recover the dominant frequency. So for the first scenario, for each this trial new from a finite set, for example, the set we choose is from -half to half, and the current sensing algorithm for each this new, we solve the optimization problem. It returns the trial solution, and in the final, the optimal new is the one with the minimum 1 norm of the frequency signal. And the accuracy of the dominant frequency in the end is O sigma 1/n. And here the sigma is determined by noise, the frequency gap, and the non-dominant part of the signal, or the off-grid components. So that's basically kind of I explained the algorithm or the main ideas in kind of relatively plain language. So in last part, I want to show you some numerics that show the algorithm kind of works. So here, two examples is we use the IC model and the Hubbard model on 8 sites. This on 4. Okay. Oops. And we just because for these two simple models, you can solve it like exact diagonalization. And we approximately prepared initial state, which has roughly 10 dominant components. And here the probability can be tuned by this parameter alpha. So we compared it to the other three, three QP, like early QP algorithms for early fault tolerance algorithms. They are kind of also the first two. This also solving some kind of fitting, very similar to our algorithm, but with some small differences. And there's another newer work. This is their new work, and it's called QMax. It's using some Gaussian filter function to do. So we compared basically for these two models. We choose different alpha here. Alpha, this corresponds to roughly this correspond to the. So for the QP problem, we focus on ground state energy. And for the IC model here, this alpha 1/8 is roughly corresponding to 87% initial overlap, and 1/4 roughly is 75% overlap, and 1/2 is about 50% overlap. And as you can see from for both these two models, actually the computer sensing based algorithm we have has slightly better accuracy, and especially as the initial overlap is large, this difference is more obvious. And so in terms of the runtime cost, here we showed with the Tmax, where basically you can think it is the length of the signal roughly. And we just show the comparison between Tmax and also the total time in the first graph. So this one, as you can see, basically they are kind of comparable, roughly the same. And a little bit different is the second chart. Here, this is the number of time samples we use in our algorithm. So for this one, compared to the other options, we have a fewer like a time sample. That's in some sense is expected because one of the features of comparison sensing is it's you only need very few time samples to recover the signal, and yeah. But the overall runtime is larger. But this is for early fault tolerance quantum computers, meaning that it's you kind of sample, you have fewer time samples. For each time sample, you can run a little bit more for each time. So it's in some sense it's more experimentally friendly in a sense. So basically that's all the main things. And here just the last slides that talk about some of the features that in our algorithm and also some open questions. So the basic feature is so the computer sensing based QPU algorithm is non-adaptive. And so we first collect all the measurements first, and you do the post-processing all at once. So you don't have to, for some of the algorithms compared to before I shown, some they have this hierarchy structure, like it's kind of adaptive in some sense. And also this one numerically to show requires comparatively fewer time samples from a discrete set. That's very helpful for early fault tolerant quantum computers. And another is if we assume the dominant frequencies, they can be shifted to become nearly on grid. And we has no like particular requirements on the initial lab. It does not have to be bigger than 50%. There are a few open questions. So first of all is for this, actually in this one, it's relatively you have strong assumption on the dominant frequencies. So one thing is we want to see if we can relax this further. And another thing is right now for the grid shift parameter we are using, we're doing kind of a grid search. Basically you give a interval and then you just divide it into a grid, then you search one by one. So it's not that bad, but it's not the best that we want. So basically, there should be a way that find the optimal grid shift parameter by optimization instead of grid search. And lastly, so for right now, our algorithm is mainly works for just QP. It's a one single phase estimation, but it should be able, we should be able to extend it to a multiple phase estimation. Of course, that's a much harder problem, but should be able to do that. So with that, thank you for your attention.